Welcome, everyone. I'm Elizabeth Trellick. I use she, her pronouns, and I'm a member of CHOP's Data Education Collaborative. I sit on the ARCIS education team in DBHI. Today's talk is the fourth in our five-part series on SQL. Today's webinar will be recorded, so please leave your cameras and mics turned off until the question time at the end. If you do have questions that come up during the talk, feel free to put them in the chat. I will be checking it, and I have colleagues on this call who will also be alerting me to questions that I need to answer. Right, so with that, let's get started. Today, we're going to be learning how to do some more advanced SQL queries on single tables. This is going to be a hands-on webinar. We'll be writing some real SQL code, and if that sounds daunting, don't worry, I'll be providing plenty of scaffolding, and we'll work through things together. In the last webinar in the series, my colleague Rose Franzen taught you how to compose single queries with select, where, from, distinct, as, and order by. Today, after a quick review of some of those commands, we are going to learn how to write more complicated queries using case, like, and group by. And along the way, we'll learn about some aggregate functions as well as practice and refresh the skills you already know. I want to thank Joy Payton and Peter Camacho for writing the material that this talk is very closely based on. It is an asynchronous learning module called SQL Intermediate. There's a link here in the slide. And I also, in addition to thanking them, want to emphasize that because of time constraints, our webinar today is not going to cover all of the topics in that module. We simply won't have time. You'll see we'll hit up right against 1 p.m. at the end. So please check out that module after this session. There are things in it we will not be touching on today. We're firm believers that the best way to learn is to practice, and as I mentioned before, we will have opportunities to practice writing our own SQL code today using a fake patient database. There will be some short quizzes for you to practice your coding and solidify your understanding as we go. So with all of that being said, let's jump right in to our brief refresher. So as we learned in the November, December, and January sessions, SQL, or SQL, stands for Structured Query Language, a programming language used to interact with relational databases. Relational databases consist of many different data tables, or can consist of many different data tables. Today, we'll only be working with the data from one table at a time, even though there are 3 tables we're going to be seeing in our single relational database. To learn more about combining data from more than one table, be sure to catch our final presentation in the series on SQL joins, which is happening next month. We'll share the dates for that on our final slide. I'll remind you some of what SQL is great for. It's great for working with rectangular data that's stored in tables with rows and columns or fields. We'll be using columns and fields interchangeably. However, SQL is not so great for fine-tuned statistical, linguistic, or data visualization purposes. It's a tool that's often partnered with other tools like R or Python, which are better suited for work like statistical analyses. We will see some of the ways that SQL can generate simple summary statistics today, but it's not going to be the best tool for your more complicated statistical analyses. Another thing we're going to see today is that SQL is technically not just one thing. There are a variety of different implementations. And although all SQL implementations have a similar structure, the same basic syntax, each different SQL database product often has its own minor variations in dialect. Colloquially, people often refer to different SQL dialects as different flavors of SQL. We've listed some of the popular flavors of SQL on this slide, and the most common difference between these flavors is going to be the availability of different functions that users can use for data manipulation, but even more importantly, the types of error messages that will be returned to the user when running code with syntax issues. There are going to be a few times during this webinar when I will point out that the flavor of SQL we are using today is impacting the outputs we get. So because we have different flavors of SQL, When you're troubleshooting, it can be particularly important to include the name of the flavor you're using with your search terms. The form we're using today actually runs in your web browser as you look at these pages. So if you have opened these slides on your own web browser, you can run the code in any of these code blocks. This lightweight SQL engine is called SQL, and we pre-populated some tables for you to experiment in this presentation. The tables you're going to see are filled with fabricated data. They're meant to look a little bit like an electronic health record, but rest assured this data is completely invented, although it was invented to look somewhat realistic. Okay, so before we learn any new SQL commands, let's do a quick review of the commands select, from, and where that we learned about last month. The basic structure of a SQL query is that you select fields from your table, and you can call your table with this dot notation with the data set name, dot the table name. And you can add conditions where a conditional statement is true. So to start exploring the patients table from our SQL database, let's first take a look at the whole table using the asterisk as a wildcard to select all of the fields. So I'm going to run this code. And as I run it, there's a few things I want to point out about running code in this webinar and in these slides, which is that this play button right here will let you run the code that is in a code box. You will get a message here, either that your query execution was complete or any error messages. And then the results will show up below. And you can click on this results of query line to collapse those results or expand them again. And if they're too wide for your screen, you can scroll side to side to see them. All right, so I'm going to collapse these results. And the next example we have is that once you know what fields you have or what column names you want, you can request just those. We can select the ID, address, city, county, and state fields from the patients table. So let's run this code, and you can see we only see those relevant ones. You might notice that we're using comma first notation here. That is our recommended notation, and that instead of saying just the name of the field, we're mentioning the table it's coming from every time. This is going to be particularly important next month when we learn about joining information from two different tables. So we want to get in good habits now. Okay. The last thing I want to remind us of before we dive in is that you can then filter which rows you see using a where statement. So I could say I want all of these fields, ID, address, city, county, state, for the patients table, but I only want the rows where the county is Suffolk County. So if I run that, I only get those two rows. We'll also be seeing distinct and order by functions again today, and we'll review them when we get there. But with our select, from, and where, we're ready to get started learning a few new functions. Okay, so let's explore some of our tables a little more deeply. And I want to take a look at the observations table. So if I select every field from the observations table using this asterisk, but I only look at the ones where observations are about peanut immunoglobulin antibodies in serum, I'm going to get 3 rows. And let's take a look at these a little more carefully. So we've got some data on when this was observed, patient ID, an encounter ID. These are all the ones that have the description we want. And then we have an observation value. It's 26.6, 37.3, 12.1. And we have units listed. This is numeric data. But we might want to know a little bit more about that. That's not the most helpful way to understand these observations. Often when you're working with data, you're going to come across the need to define your own custom categories or groupings. Is 26.6 good or bad? Well, you're probably not going to categorize it as good or bad, but you might have to define it as either normal, borderline, or abnormal. And it might be a lot easier than just having some number breakdowns memorized, rather than having to look at a line and say, oh, 12.1, that's borderline, maybe. We can have SQL tell us that using a case statement. So what we're going to do with case statement is first I'm going to talk about some of the theory of this, and then we're going to see it in action. The case statement is used to produce conditional row-level output based on columns or rows provided as input. It's like an if statement in other languages, but with multiple possibilities or cases that are considered. So we're going to take a look at a generic example, and then we're going to practice with our observations table from our data set. One way to think of a case statement is by its components. So here I've got a statement written out and broken down into 4 components. But this way of thinking of them as components 1, 2, 3, and 4 is not actually how I like to think of a case statement. So while I'm showing you this, so you can refer back to it, I'm going to walk you through the way I like to think about a case statement, which is from the inside out. So let's take a look at that. The inside of a case statement is based on when-then conditional statements. If you're used to other programming languages, you might be used to if-then statements, and this is really similar. So when a conditional statement is true, then some designated output will be returned to you. You can have as many conditional statements as you want, but be aware that for each row, SQL is only going to return one output corresponding to the very first time a condition is true. So let's say we were considering the patient's age field. That's not actually a field that's in our patient's table, but it's one that's pretty easily understandable. So if we had a row where the patient age was 10, these when-then statements would evaluate that. The first when-then statement would say, it is not true that that age of 10 is less than 1. So it would move on to the next one. And would say, it is true that that patient age of 10 is less than or equal to 12, and return the child category. You might be wondering, but it's also true that 10 is less than or equal to 17. Is it going to return child and teen? Both of those are true. You actually don't have to worry about it returning teen, because as soon as it returns a true then for one of these statements, it's going to stop checking the previous ones. So even though 10 is less than 17, a row is not going to be categorized as a teen because it's already been put in the child category. Okay. If none of your conditional statements are true, then an else statement is going to tell SQL what to do in that case. If you leave it blank or omit it, or sorry, if you omit the else statement entirely, SQL will think of this as being an else null statement. It's just going to return none of these were true, a null value by default. But we strongly encourage you to always use an else statement, even if you would like the value to be null. It's going to make your code more explicit, both for you looking back at it later and any colleagues who are trying to debug it later or change it. Once you have the inside, which is all of your conditional statements, you need to wrap your conditional statements, their when-thens and your else, inside case, which opens it, and end, which closes it. The indentation before each of the when statements and the else statement are for us as human readers of this code. SQL doesn't need those lines to be indented, but it makes it a lot clearer to us when we're looking at this block of code to see where it starts and ends. Okay, so like I said, we've started with a lot of theory because case statements are complicated. But let's return to that observations table and see how using a case statement will help us understand that peanut IgE antibody data. Okay, so what I've set up here is a case statement that includes what these numbers mean. So if that observation value is greater than or equal to 17, then that is a strongly positive result. We have similar numbers for positive results, equivocal results, borderline results, and negative results. The case statement itself goes between the select statement and the from statement. So let's run this and see what happens. All right. Come down here, and now we've got a new column that returns that 26.6 is strongly positive, 37.3 is also strongly positive, and 12.1 corresponds to a positive interpretation of that number. That's a lot easier to read down here, but it's suddenly pretty hard to read up here because our column name is just the entire case statement. Well, we can fix that by adding an as new column name after the end. So let's do that. Follow that closing end with the word as and a new useful column name. So I'm going to come in here and modify this code as interpretation. And let's run this again. All right, and now our results look a lot more readable. We have nice, informative column names, and we know what these numbers correspond to in terms of positive, strongly positive, and that they don't correspond to the other values. All right. It's always a good idea to close your case statement with an as after the end, like we just did, because otherwise it's just going to be hard to read your results. I want to pause here for some questions before giving you your first opportunity to practice these case statements in a real SQL environment. So I'm going to take a look at the chat. I see there's a question, why the comma before case? So let's go back up here and take a look. So the question was, why is there a comma right here before case? And the answer is, the reason the comma is before case is a style choice, but there does need to be a case between a comma between the select statement and the case statement. We could put the comma at the end of the observations line, closing the select. You could run that again and get the same table. And to confirm that we're running it again, this number of how many times we've run it has changed. I can move forward and back and change it. But our style guide that we prefer, and this might not be the one that your lab prefers or that your colleagues prefer, so defer to the thing that will make your code most readable for the people you're working with. But what we recommend is this comma first notation, so that if you were to copy this somewhere else, it would already have the comma in the right place. Yeah, that case statement is essentially acting as another field. That's why you need the comma. The case statement ends up being this last field, and that's also why we needed to give it a name. It's the interpretation field. Excellent question. All right. So with that, I'm going to move on to your first opportunity to give this a try yourself. This is the Your Turn 1 example, and I'm going to ask my colleague to put a link in the chat to Your Turn 1, which will bring you right to this page. So imagine you're studying attitudes about smoking, and you're going to issue a survey in phases. Phase 1 is going to go out to the residents of Plymouth County. Phase 2 will go out to the residents of Essex County, and Phase 3 is going to go out to Barnstable County. What you want to do is finish this following query. in such a way that you get the patient name, county, and a new column called phase. I'm going to give you a few minutes to try this on your own, and there's going to be a comment in the chat for you to like when you are done. Once we have quorum, we will complete this query together. So don't worry if you struggle with it. We are going to go through it all together. All right, I see we have about 10 people who've completed the query. I know some of you are probably still working on it. Because we're a little bit crunched for time and the amount of things we're doing, I'm going to start demonstrating how we would complete this query together. So we want things to be true. We want when the patient's county is equal to a certain string, then we want to return phase one. And that string, phase one, will go out to residents of Plymouth County. So let's copy that directly in here. Similarly, phase two, we want patient's county, and I'm seeing I have a typo. County is not count. When that is equal to, let's see, phase two is Essex County. Then I want to return phase 2. And lastly, when the patient's county is equal to Barnstable County, then it's phase 3. And if I run this now, I will get a result, but it's not going to have that new column called phase. It's going to have that big messy one over here. So I've got my phase 1, phase 2, but I need to end with as phase at the end in order to get a nice heading for that field. If you're looking at these slides later after this session, there is an answer at the end. Please don't reveal them while you're going through them in the webinar, but they are there to help you if you come back to them later or share these with someone who couldn't make the webinar. All right. I don't see any questions in the chat. Please don't hesitate to type them in if you've got any. But because I don't see any, I'm going to move on to our next function. That is like. So far, every time we have created a query, we have needed to know exactly the form the data in our table takes. You saw I copied those county names directly. And that worked because they matched directly what was in the table. But let's take a closer look at the allergies table to see what I mean by knowing the names exactly. And I see a question in the chat. Does text need quotes around it while integers do not? Yes, that is true. Text is going to need quotes around it, and if your data is stored as a text, even if it is an integer, you might also need quotes around it. This can be an important thing to pay attention to of how SQL is storing your data. Right. So I'm going to continue with like. I see there's a specific question that I'm going to ask my colleagues to give a shot to in the chat. So we've got all of these different distinct allergy descriptions. And let's say we're not interested anymore in this allergy to peanuts. We are interested in allergies to pollen, maybe both grass and tree pollen, but also if anything else is there too. We could, if we wanted to, select all of the rows that correspond to grass pollen allergies or tree pollen allergies. We could do that using a where statement, but it's going to require us to know exactly how those are spelled out, allergy to tree pollen, an allergy to grass pollen, and it's also going to require us to know that there are no other pollen allergies in this table. In this very small table, we happen to know all of that, but we might not in general. So let's take a look at how we could deal with something like that if we wanted all pollen allergies, whether or not we knew what they were. And just to emphasize why it's really important that you be able to do this, if these data were entered by hand, the same allergy might show up as both allergy to grass pollen and grass pollen allergy with different wording or different capitalization. Or maybe a new patient has come in with new different pollen allergies. In that case, you don't want to have to update your whole query to get the data you want. And that interferes with one of the main reasons we write scripted queries like this in the first place. For reproducibility purposes, you should be able to rerun your query even if the data has changed and there are new categories that you want to appear. So how can we get all of the pollen allergies without us having to perfectly type them out in a very long where statement? This is going to bring us to the like operator. The like operator lets you compare textual data to a pattern rather than checking if two strings of characters are exactly equal with an equal sign. This action is known as pattern matching, and it can let you filter on row values that are similar, but not exact matches. Right. So, the like operator uses two distinct wildcard characters that let you make patterns where some characters are unknown. The percent sign is the wildcard character for 0 or more unknown characters, and the underscore is going to be our wildcard for exactly one character. These let us build patterns to compare with a string of text data. So let's take a closer look at some examples using the word pollen and our percent sign wildcard. If we put a percent sign before pollen, that's going to match allergies to tree pollen because we have some characters, the whole allergy to tree with 3 spaces in there, and then the string pollen. Alternatively, if we put the percent sign after pollen, that's going to match pollen allergy-trees. But in most flavors of SQL, it's not going to match capital pollen allergy-trees. Because most flavors of SQL are going to care about that capitalization. We happen to be working a very lightweight one that doesn't, but anything more powerful than this very lightweight a la SQL browser is going to care about capitalization. If we put those percent signs both before and after the word pollen, it's going to match allergy to tree pollen and that lowercase pollen allergy-trees, and also tree pollen allergy. It has characters both before and after the word pollen. So we need to surround this pattern we want to match with quotes and use that like operator instead of the equal sign. So we would say allergies.description like percent pollen percent, or like in double quotes, that same pattern. All right, so let's see this in action. If we put that our allergies.description is like that pattern where we have some characters and then pollen and then some other characters or not, we get all of our grass pollen allergies and all of our tree pollen allergies. And if new data is added where someone says pollen allergy to trees or pollen sunflowers, that's going to show up too. Okay, but I said that many flavors of SQL are going to balk at having a capital P in pollen. What if someone enters new data where pollen is capitalized and like is caring about it? Well, in that case, you can wrap the left side of your like statement in a lower function to make sure the query returns both capital and lowercase versions of the pattern. So what that's doing, if I come back up here and put that in, if I put lower around allergies.description, it's going to compare not the string here, capital A, allergy to grass pollen. It's going to compare what happens when you make all of them lowercase. And in this example, you're going to get the same results. I want to pause here for any questions before I hand it over to you for the second time it's your turn to practice this on your own. So I'm going to come over into chat and see if any questions have been raised. Yes, I'm seeing that question. The equal sign matches strings, but only an exact match. So it wouldn't work if you have capitalization that's different or punctuation or even different spaces going on there. but like will let you get around that. Okay. So I'm not seeing any other questions. I'm going to ask my colleague to copy the link into chat for your turn 2, where you can navigate there in a browser already open to. So let's say you'd like to research patients born in the 1970s. So any year starting in 197 something should work. Use a like statement to enrich the query below and find the patients that you care about. An important thing to notice here is that, or an important thing for me to tell you, is that the birth dates are strings. Even though they could be other types of data, like a date, in this table, it is a string of characters. So once you have given that a try, if you've completed it, please like this comment. And once everyone's gotten a chance to give it a try, I will go through and do it all together. I'll give you a minute or two to take a crack at that. All right, looks like we've got a good number of you who've completed it. Again, if you haven't, that is just fine. We're moving a bit quickly today. So before I enrich this query, I want to run it as is, just to show that birth date, we have that year first, and then we've got some other stuff. So this first one would start 197 and then have some other characters. This starts 199 and then has some other characters. So the pattern we're trying to match, oh, did not mean to go to another page. The pattern we're trying to match is where that patient's birth date is like, and the string we want is going to be 197, and then a number of characters after that. So using that percent fine. Let's run that. And we see we get 4 patients, all born in the 1970s. Great. Are there any questions on this? I see we've got a great answer coming from one of my colleagues about that between function. Okay, well, let's look at another type of data we can collect from a SQL table. I want to talk about aggregate functions. Aggregate functions can be used to get a single value related to the values for multiple rows of data in some meaningful way. This aggregation could be a numerical statistic, like the sum or standard deviation of a number of rows, or it could pull out a special value, like the minimum or maximum value. It's going to work as well for strings, in which case it would be the first or last value in alphabetical order. There are many other possibilities as well, like giving a count of rows or pulling a value at random from the rows. But I want to show you some of the most commonly used aggregate functions for us to practice on. The count function is going to return the count of the number of non-null values among the columns and rows provided as input. Sum adds up all the values, provided that those are numerical values. Min is going to return the minimum value the column provided. Max will give you the maximum, and average will return the numerical mean of all of the values in the column provided as input. To count all of the rows in the table, you can use that count asterisk. Same way we use the count asterisk, or the asterisk as a wildcard. So let's run this and see what we get. Count asterisk is total rows, count patient's birth date as births, and count patient's.death date as deaths. If I run this code, I now have this tiny little table with 3 fields. The total rows is 25. The total births is also 25. Every row has a birth date. But the total deaths is 5. Only 5 of those have death dates. Most of them have null because the patients are still alive. SQL is going to do its best to aggregate the data no matter what is going on. So even if you have different types of data in your column, it's going to give you what it thinks you're looking for. The outputs might make the most sense if the type of data is what the function expects. For example, if we run a sum of the patient expenses, we're going to get a sum of all of their numerical expenses. I mentioned before that maximum for a string will give you the last alphabetic name, and minimum will give you the first, even though here this means last name and first name. Average of their coverage. Let's take a look at what we get. So here I didn't use an alias because these are fairly simple. Sum of patient expenses is this big number. The maximum last name is alphabetically with the last name that comes last, which starts with a Z. The first name of all the patients that comes first starts with an A. And the average in the patient coverage is this number here, which I want to point out is way overly specific in a non-helpful way. This is just a floating point error. That 0.00001, that's not actually relevant or real. But because of the way it's computing it, it's giving you this extra remainder. Okay. We can also see how SQL tries to adapt by changing what columns we're taking the sum, max, min, and average of. So what I'm going to do is change all of these to the column sex. The sex column here is just the letter M or F. So this is a time when the fact that we're using a la SQL makes a difference. A la SQL doesn't really know what to do with sum, so it concatenates them. That's completely useless. Max and min, it's taking the alphabetical order. That's what we expect it to do. And average, here we're getting a null value. Nothing's showing up in our table. But that's only because our flavor, a la SQL, says, oh no, I can't aggregate this. I'll just give you null. Many other flavors of SQL are going to give you a helpful error message. It will tell you something like, you can't take the average of text data. And that's going to help you improve your query to get useful information. Okay, so if we can get these statistics, these summary statistics out, like total births and deaths, you might want to aggregate by that. So I called those aggregate functions, but we might want to group and say, actually, I don't care about all of the birth dates unless I can sort them by patient sex. I only care about how many male births and how many female births there were. It doesn't help me to know the total number. So previously we've seen some theory and then examples. Here we're going to do an example first and then learn the theory of what's going on. So this set of code, we're selecting patient's sex. We're counting the birth dates as births. We're counting the death dates as deaths. And then at the end, we have this group by patient's sex line. So if we run this, we now have our same we have our three fields, sex, births, and deaths, like we expect. And we're seeing our rows. M has 10 births and 2 deaths. F has 15 births and 3 deaths. So you can see how this could be really useful to collapse that data into male and female or another grouping. I find that it helps a lot to start with the group by clause. So let me show you what I mean. Every aggregate function can give one and only one value for the entire group of rows. That means the only things you can ask for in the select statement are things you've grouped by, like patient sex. We've already grouped by patient sex, or aggregate functions like count, or average, or min, or maximum. Even if your grouping happens to all have the same, say, race, it couldn't return a race if you selected that field because it doesn't know a priori that you've grouped by race, because you haven't, unless you explicitly tell it. So let me show how you could do that in action. You can group by more than one field. So if I also wanted to group by race, I would have to group by it at the end in the statement. And then having done that, I'm allowed to select for that up here in my select statement. So let's run this. And now we can see that births and deaths are grouped by sex and race. So there are 4 white male births. There are 6 Black female births and 1 Black female death. And similar to what we saw with the distinct command last month, we're not actually seeing every combination, every possible combination of male and female with a race. There aren't any male other patients. There aren't any male other rows. So it's not returning that to us. It's only showing us ones that actually exist. Okay, so I see there is a comment. Can you sort the output so that they're grouped by sex first, then race? You absolutely can. We're going to do that in about 90 seconds. Great question. All right. So you can see that there are only 2 types of fields in our select statement, either the things we've grouped by or the aggregate functions. So now let's lead to the excellent leading question. What if we want to sort this? This table is nice, but maybe we've got hundreds of different things showing up in our group by groups. So the first thing I want to show you is the having clause. Having can be used to filter your result set on a value of the aggregate function. It's a little bit confusing because it seems very similar to where. The same way that where can filter rows of a select statement, having filters rows of a group by statement. So it comes after group by, and I'm going to run this code counting the population in each county. You might say, hey, we actually don't want our data to come from Bristol County or Worcester County that only have one patient each. So what we can do is we can say only show me, using this having count greater than 1 statement, only show me rows where this count is greater than 1. And if I run this again, those two disappear. You can also then, to get directly to this question, use an order by statement. So we saw that last month. An order by statement lets you order by either one of your fields. I'm going to order by subject population. And let's see what happens when I run that. Now it's ordering by subject population from smallest to largest. Change that largest to smallest. I could alternatively have ordered by county alphabetic order. All right. So I want to pause here because I see that there are some questions in the chat. And I see my colleagues are answering them. Yeah, whatever you order by had better be in your select, otherwise it can't order it by it. And yeah, you could have grouped that previous query by sex and then by race, or by race and then by sex. See, how would you order this table so that we see the counties with the largest subject population first? I believe that is going to be the ascending ASC, and let's see, that do it for me? Nope. That is something we touched on last week.
I think it would just be DSC, right?
Oh, DSC, because
the
it's
highest
DS.
to the, or DESC.
You're totally right, because it,
Yes.
Nope.
It's an E. If there's an E in there, I mistyped it or said it.
Thank you. Yeah. Yeah, so I think we saw last month, and they were not at the top of my brain today, but you can order ascending or descending using ASC or DESC at the end of that. All right. And I see it worked for you as well. Excellent. Okay. So last thing, you can use the having statement to filter, the order statement to order it by county. We could also have done it by patients county, which would then alphabetize it, or because I put descending, anti-alphabetize it. So we've got 5 minutes left, and what I want to do is have you create your own SQL query completely from scratch. The previous 2 turns, you were filling in things that were already there. For this last turn, I'm going to have you create a query completely from scratch, but it's going to be very similar to that last example we did. So your challenge is to create a query of the LSQL.patients table that gives the patient population of each city which has more than one patient living there. Give the results in an alphabetized list. And a big hint for this and for every SQL query you do is that you don't need to write the entire query at once. Try first writing a query that returns some of what you want, like the count of patients in each city, and then modify it to get the query that you want. So I'm going to put a comment to like once you've completed it, but I'm really only going to give you a few minutes because we only have a few minutes to give it a try. See, a few people have completed it. I know most of you are probably still working. This is much longer to make a query from scratch. Instead of going through it all together, because we only have 2 minutes left, I just want to give you a quick review of what we've done today and leave completing this Your Turn 3 as some homework for any of you who haven't done it yet. And I will stay on after this call if you want to go over it together, or you can also check a answer once you're done. But just to recap what we've done today, we learned about the case statement, which uses case, when, then, else, and end to return different values based on a conditional statement. We learned about the like statement, which lets us compare patterns of characters in more complicated ways than finding an exact match. And we saw the lower function to make everything lowercase. There's a similar upper function to make everything uppercase. We learned about 5 aggregate functions. There are many more. These were the most commonly used we wanted to introduce. And we learned about grouping by to collect rows into groups with matching entries in a particular column or columns. And having grouped by that, we can use the having function to filter for only groups that meet a certain condition. I want to emphasize there's many additional resources out there. This was only a 1-hour webinar, so we're only able to cover so much. But you all have the links to all of these slides. And there are upcoming sessions next month. The next one is March 12th. We'll start combining information from multiple tables and SQL joins. And everything from this talk and more is in the SQL Intermediate level online self-paced tutorial. And our GitHub repository for all of these materials contains these slides. It contains all of my speaker notes. And shortly, it will contain a recording of either this or earlier in this month, the same SQL Intermediate talk. So thank you so much for spending your lunch hour with us. I know your time is super valuable. I hope you found this worthwhile. And I'm going to hang around. Feel free to hang around and ask questions or sign off. Thank you so much for attending and your excellent questions.